At what point does the brand step in and go, right, we're opening a lawsuit against you, and I don't want it to ever become like corporate?
The car was never supposed to come back to life. A $4 million carbon fiber hypercar, written off after a violent crash, was locked out of its own manufacturer's ecosystem and written off as structurally and economically finished. Yet inside a workshop far from Bugatti's controlled facilities, Matt Armstrong did the unthinkable. They rebuilt it anyway. Not through factory support, not through official parts channels, but through engineering workarounds, fabrication, and sheer persistence. And it wasn't easy. Today, we'll unveil the amazing story of how Alex Gonzalez and Matt Armstrong won against Bugatti. Supporters say that this is a victory for the idea of ownership as a whole. Let's start from the very beginning. The crash, buyback, and project origin. This wasn't just another crashed supercar. It was one of roughly 60 examples of the Bugatti Chiron Pure Sport ever produced, each leaving Molsheim with a starting price in the region of $3.6 million before options pushed it even higher. Beneath its sculpted carbon body sat Bugatti's defining engineering statement, an 8.0-liter quad-turbocharged W16 engine delivering around 1,500 horsepower. Developed under the Volkswagen Group era and sharpened for the Chiron lineup, the Pure Sport variant was not built for top speed records alone. It was reworked for precision, shorter gear ratios, reduced unsprung weight, and revised aerodynamics, everything tuned to make a 2-ton hypercar behave like something far more agile. It was the distilled result of years of research, engineering, and excess, turned into one of the most extreme road cars ever sold. One of those 60 cars ended up in the United States, owned by Florida-based influencer Alex Gonzalez. By 2024, this Bugatti existed as much on screens as it did on asphalt. Videos, posts, appearances. But visibility cuts both ways. When something goes wrong at that level, it doesn't stay private for long. The shift from spectacle to disaster happened in seconds. It wasn't a high-speed loss of control or a dramatic track incident. It was something far more ordinary. Traffic compressing unexpectedly, brake lights stacking ahead, and one vehicle failing to react in time. The impact came from the rear, but it was the Chiron's front end that absorbed the force, collapsing under the load. Carbon fiber panels fractured, splintered, and tore away, revealing the complex structure underneath. What followed was a cascade of failure across systems. The headlights were destroyed instantly, the front-end geometry thrown out of alignment, and the carefully engineered airflow structures compromised. Inside the cabin, airbags deployed, sealing the moment as more than just cosmetic damage. Early repair estimates placed the cost of restoration through official Bugatti channels at around $1.7 million in parts and labor. That number alone was enough to redefine the situation. When a Bugatti technician traveled from Europe to inspect the car, it was a high-level assessment of whether the vehicle still belonged in the category of repairable machines. The verdict followed the logic of the industry. The damage wasn't superficial, and the cost-to-repair ratio crossed the threshold insurers use to make final decisions. Despite its rarity, despite its value, the car was classified the same way any heavily damaged vehicle would be under those conditions. It was declared a total loss. The damaged Chiron was then released into the salvage pipeline and entered Copart, the well-known auction network where insurance write-offs are sold to rebuilders, exporters, and specialists. But then, Alex Gonzalez, known online as FXLXG, did something unusual. After the insurance payout was processed, he bought the car back from Copart. The reported purchase price was around $1.6 million, with total cost including fees rising to approximately $1.9 million. This may seem ambitious in retrospect, but back then, all he had done was effectively pay millions to reclaim a heavily damaged version of his own hypercar. The economics alone made no sense. A damaged, non-functional Chiron Pur Sport is not an asset most people attempt to recover. But this was not a typical salvage situation. The Pur Sport variant is extremely limited, and losing one permanently reduces an already rare production pool. What followed turned the project into something far larger than a private repair job. Matt Armstrong, a UK-based automotive YouTuber known for rebuilding high-end performance cars, was brought into the project. His involvement transformed the situation from a personal salvage recovery into a globally followed engineering experiment. Armstrong had built a reputation for taking severely damaged cars and returning them to working condition, but this was on an entirely different scale. A mid-engine, quad-turbo W16 hypercar with carbon fiber structural architecture designed for factory-level servicing. Only. The damage itself was not cosmetic in any meaningful sense. Reports and documentation from the rebuild show a heavily impacted front end, destroyed lighting assemblies, compromised body panels, and critical structural concerns involving the carbon fiber monocoque and drivetrain mounting points. In vehicles like the Chiron, the monocoque is the core structure that everything else attaches to. Once that is compromised, repair becomes less about replacement and more about engineering judgment at microscopic tolerances. In short, it seemed impossible. In fact, Bugatti insisted it was impossible outside of their ecosystem. But then, everything changed. Manufacturer resistance and V1N controversy. As expected, Bugatti declined to support the rebuild process and did not supply official replacement parts for the vehicle, effectively cutting off access to its internal repair ecosystem. In hypercar terms, that is a structural barrier to restoration. At the center of the issue was the vehicle's identity within the manufacturer's system, its Vehicle Identification Number, or VIN. In this case, reports from the rebuild documentation indicate the VIN was placed under restriction, which prevented authorized dealerships from processing or supplying factory components for the car. You see, the Bugatti Chiron Pur Sport relies on tightly controlled parts networks where even routine components are not freely available outside official channels. Once a VIN is restricted, the car is effectively isolated from that system. So what began as a salvage recovery was now a locked ecosystem problem. Even with financial resources available, the normal pathway, order parts, send to authorized repair facilities, rebuild under manufacturer supervision was no longer accessible. Instead, the rebuild had to proceed outside Bugatti's controlled infrastructure. Publicly, the position of the manufacturer's side was reinforced by Mate Rimac, CEO of Bugatti Rimac. Rimac challenged the feasibility of rebuilding the car independently, particularly outside official facilities. His argument focused on safety and engineering integrity. A hypercar with a carbon fiber monocoque structure, advanced electronics, and a quad turbocharged W16 engine is not designed for ad hoc structural repair. So, on one side, the rebuild team treated the car as a technically recoverable machine, albeit one requiring advanced fabrication and reconstruction methods. On the other side, Bugatti emphasized that certain operations, particularly chassis splitting, structural realignment, and monocoque inspection, require specialized jigs, calibrated environments, and trained technicians who work exclusively within factory conditions in Molsheim, France. The implication was clear. Outside that environment, accuracy and safety cannot be guaranteed at the required level. The tension sharpened further because the Chiron platform itself is not a conventional chassis design. The carbon fiber monocoque is a single structural shell that integrates passenger safety cell, suspension mounting points, and drivetrain alignment geometry. Any deviation in repair alignment can affect high-speed stability, crash safety, and drivetrain stress distribution. However, as pressure built, communication between the parties did occur, and the initial rigidity of the situation softened slightly over time. However, the early phase of the controversy had already defined the tone. A privately owned hypercar, heavily damaged and purchased back at salvage value, now existed outside the standard repair pipeline of its own manufacturer. What made the situation unusual was not just the refusal itself, but the visibility of it. Most high-end manufacturer repair decisions occur quietly within service networks. Here, however, the rebuild was being documented in real time, turning internal policy into public debate. By the time the discussion settled into its next phase, the core conflict was clear. One side argued that the complexity of the car justified strict control over repair processes. The other demonstrated that, with enough engineering expertise and fabrication capability, alternative pathways to restoration could still be attempted. The Chiron Per Sport was now more than a car. It was a battlefield. The price? Ownership. Independent engineering approach. The workshop in Miami was never designed for what arrived inside it. There were no factory jigs, no manufacturer-approved tooling, and no support line to the original builders of the car. Yet that is where the independent engineering phase of the Bugatti Chiron Per Sport rebuild began. Since Matt Armstrong and his team were operating without direct factory support from Bugatti, they had to build a parallel supply chain. The first constraint was obvious: parts availability. In a standard repair, even high-end vehicles rely on manufacturer networks for structural and drivetrain components. In this case, that network was effectively closed. The response was to shift from procurement to production. Components that could not be sourced were either located through secondary markets or fabricated from scratch using precision manufacturing methods. This was not improvisation in the casual sense. It was structured engineering without OEM infrastructure. One of the core techniques used was 3D scanning of damaged components. Instead of relying on paper schematics or replacement part orders, technicians physically scanned broken pieces to generate high-resolution digital models. These models were then refined and used as templates for CNC machining. This method is standard in aerospace, motorsport, and high-end restoration work, where tolerances are measured in fractions of millimeters and original parts may no longer exist. But before fabrication could even begin, the scale of access required a more aggressive step. The car had to be physically split into two halves. This operation is not typical in standard automotive repair environments, even for supercars. The separation was necessary to reach the gearbox assembly and the surrounding mounting structures, which had suffered significant impact damage during the crash. The chassis split revealed the internal architecture of the car in a way that is normally reserved for factory-level disassembly procedures. Inside that exposed structure, the extent of the engineering challenge became clearer. The gearbox mounting system, which is critical for maintaining alignment between the engine, transmission, and chassis, had sustained serious damage. Instead of swapping entire assemblies, the team moved toward repair and reinforcement. This meant assessing load paths, stress distribution, and material integrity before deciding how to restore structural function without compromising the original geometry. In parallel, custom fabrication solutions were introduced for systems that had no viable off-the-shelf equivalents. Cooling systems were a major example. The Chiron's performance envelope requires extremely efficient thermal management, and multiple radiators were destroyed in the crash. Rather than sourcing factory replacements, which were unavailable due to the restricted supply situation, the team commissioned custom-built radiators designed to replicate the original cooling capacity. These were engineered to match performance requirements rather than replicate factory branding. Airbag systems and interior components also required adaptation. In documented rebuild footage, substitute components were used in certain areas where direct OEM parts were inaccessible or impractical to obtain under the circumstances. This included alternative airbag units and a full interior rebuild that restored the cabin layout and materials to near original appearance, though not necessarily through factory supply channels. The interior work was as much about restoration of function as it was about visual authenticity. Then there were the wiring and electronic systems. Modern hypercars like the Chiron rely on integrated electronic control units that communicate across multiple subsystems. When components are replaced or repaired outside factory workflows, synchronization becomes a technical challenge. The team had to ensure that rebuilt or substituted components could still communicate correctly with the car's central systems, or risk cascading system failures that would prevent operation entirely. Instead of asking, "What part fits here?" the question became, "What function must this system perform, and how do we recreate it?" You see, in a controlled factory environment, replacement is standard. In this environment, equivalents had to be engineered rather than purchased. Remember, access to parts was cut off. The most critical outcome of this approach was structural reassembly. Once the chassis was split, repaired, and inspected, it had to be rejoined with precise alignment. Any deviation in geometry could affect suspension behavior, drivetrain alignment, and high-speed stability. The reassembly process, therefore, required careful measurement and iterative adjustment, ensuring that the two halves of the carbon fiber monocoque aligned within acceptable tolerances. By the time major systems were reconnected, the car had effectively become a hybrid of original components, repaired structures, and newly fabricated parts. It was no longer a pure factory build, but it was also no longer a wreck. It occupied an unusual middle ground, mechanically functional, structurally reconstructed, and engineered outside the manufacturer's official ecosystem. However, the rebuild demonstrated that even a highly controlled machine like the Chiron Pur Sport can be partially reconstructed through advanced independent engineering techniques, such as 3D scanning, CNC fabrication, structural repair, and system integration when factory support is unavailable. It also highlighted how far modern automotive engineering has moved into a space where digital modeling and precision machining can replicate components once thought impossible to recreate outside OEM facilities. Armstrong proved that hypercar-level complexity can be addressed outside traditional manufacturer frameworks, provided the engineering capability and resources are sufficient to reconstruct both form and function from damaged reality. Of course, Bugatti remained unmoved. And so did the car. It was not functional yet, but this was also destined to change. Here's how Alex Gonzalez and Matt Armstrong won against Bugatti. The first real technical breakthrough came deep in the drivetrain. The transmission mounting system, which had absorbed significant crash force, was repaired and reinstalled successfully. This was not a cosmetic milestone. In a mid-engine hypercar, the gearbox mount is part of the structural alignment that keeps the engine, drive shafts, and suspension geometry stable under extreme load. Restoring it meant the team had re-established the mechanical backbone of the car. Once that foundation was stabilized, the next phase escalated in complexity. The carbon fiber monocoque had already been split earlier in the rebuild to allow access to internal damage, and now it had to be reconnected with structural precision. The team used high-strength fasteners, including titanium bolts, to bring the chassis halves back into alignment. This step effectively reversed one of the most invasive operations in the entire process, reconstructing a structural shell that is normally only assembled once in a factory environment. With the physical structure reformed, attention shifted to systems integration. Fuel delivery, cooling circuits, and electronic control units were reassembled and synchronized. In modern hypercars, these systems do not operate independently. They communicate constantly through a centralized control architecture. A mismatch in calibration can prevent the engine from starting entirely. Bringing them back into sync meant restoring not just hardware, but digital coordination across multiple subsystems that had been disconnected, damaged, or replaced during the crash. Then came the moment that defined the project publicly: the engine start. After weeks of structural repair, fabrication, and system integration, the W16 engine fired for the first time since the crash. In mechanical terms, this confirmed that compression, fuel delivery, ignition timing, and electronic control were all functioning in harmony. It was the first proof that the car was no longer just a collection of repaired parts, but a working system again. That success quickly escalated into something more visible. The car was able to engage the gear and move under its own power. This step mattered more than it might appear on the surface. Because the Chiron Per Sport is nothing like your average car, movement confirms that drivetrain alignment, transmission function, and electronic coordination are stable under load, not just at idle. For a vehicle that had previously been declared a total loss, this meant that Armstrong had just revived a dead car. Despite that progress, the rebuild remained incomplete. Even as the car ran and moved, multiple systems were still under refinement. Interior restoration work was ongoing. Cooling systems had been rebuilt or replaced with custom solutions, and various components still required adjustment. The car was operational but not finalized in a factory-equivalent sense. This distinction is critical. There was no confirmation that the vehicle had achieved factory-level certification, safety validation, or full road legality. In other words, while it functioned mechanically, it had not been verified through the formal standards that govern production vehicles from Bugatti's engineering and safety protocols. That gap separates a working rebuild from an officially sanctioned restoration. Even so, the achievement was widely recognized in automotive circles as a major milestone. Running and driving a hypercar of this complexity after a severe structural crash is not routine. It requires not only mechanical restoration, but also precise alignment of digital, hydraulic, and structural systems that were originally designed to be assembled by Bugatti only. The broader impact of the project became impossible to ignore. The rebuild had evolved into one of the most visible automotive engineering stories online, drawing attention far beyond enthusiast communities. It exposed the tension between independent repair capability and manufacturer-controlled ecosystems. Bugatti had maintained throughout the process that complex structural repairs require specialized facilities and trained technicians. The rebuild demonstrated that, under certain conditions, even highly complex vehicles can be partially restored outside official channels. Through scanning, fabrication, structural repair, and system integration, the team proved that functionality could be recovered without factory intervention. And that is where the story stops being just about a car. Ownership, at its core, implies control. When someone spends millions acquiring a machine, the expectation is that the object belongs to them, not just in title, but in decision-making. This project forced a difficult question into the open. Does ownership end where manufacturer control begins, or does it extend to the right to repair, modify, and rebuild, even at this level of complexity? The work carried out by Matt Armstrong and Alex Gonzalez didn't resolve that question legally, but it made it impossible to ignore. It demonstrated that with sufficient expertise and resources, the boundaries set by controlled ecosystems can be challenged. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.